Hello, this is the continuation of chemical kinetics. We will do collision theory, Maxwell-Boltzmann energy distribution diagrams, activation energy, potential energy diagrams, and also reaction mechanisms. Let's start with collision theory. Collision theory will help us to understand how the speed of the reaction is affected by several factors. With this theory, the speed of the reaction is proportional to the number of collisions between the reacting molecules. But the collisions must be effective. That means the collisions need to yield products. When we increase the concentration of reactives, we increase the chances of collisions, including effective collisions. So, how do we produce effective collisions between particles that are reacting in a container? Well, it will depend in the molecular orientation of these particles, of these molecules. So it's really important to understand this factor, because when two reacting molecules or species collide, they must have the right molecular orientation and they must have the right amount of potential energy and kinetic energy to have a successful formation of chemical bonds to make a product. Let's check this diagram, and also I'll suggest watch the video. It's an animation on collision theory showing different situations where molecules collide, but not always the collision is going to be effective. So the right orientation for the collision and the right amount of kinetic energy are two important factors to produce the effective collision. The minimum amount of kinetic energy that these particles must have is called activation energy, E sub A. If the particles that are colliding don't have the right activation energy, they will not produce a chemical bond, even if they collide with the right orientation. The other situation can happen too. Two molecules are colliding and they collide with the right orientation, but they don't have the right amount of activation energy to form that bond, to produce that reaction. In that case, no new molecule is being formed. So yes, we need both. We need the right orientation and we need the right amount of activation energy to form a new bond, to break all bonds and to form a new bond. Maxwell-Boltzmann energy distribution diagram will help us to understand how the energy and the activation energy will form the bonds. In this diagram, as you can see, we have two different graphs there at two different temperatures. And this is a graph of fraction of collisions with a given kinetic energy. That's the y-axis here. Fraction of collisions, the number of collisions here with a given kinetic energy. And the kinetic energy depends on the temperature. What is temperature? Temperature is the average kinetic energy of molecules. As you can see here, the curve for T1, which is the blue, has less energy, less kinetic energy than T2 curve, higher temperature. T2 is bigger than T1. So particles here will have greater amount of kinetic energy. And this graph shows the distribution of these particles with given potential energy. Notice that for T1 curve, most numbers of particles will be under this curve here. This area, the blue area, the area under the curve for T1 in this range of kinetic energy shows number of particles having that average kinetic energy. Most of the particles are under this under the area of this curve. At that temperature, very few molecules here in this area. The area under the curve here shows the fraction of molecules that reach the minimum kinetic energy for the reaction to occur. And this minimum energy needed for the reaction to occur, which is a kinetic energy, is what we call the activation energy. In other words, a system running at temperature 1 will have only very few molecules with the right amount of kinetic energy, with the right amount of activation energy. So these molecules here have more chances to produce effective collision if they also have the right orientation when they collide. Most of the molecules at temperature 1 will be here in this area. In other words, most of the molecules have no chance to produce an effective collision because they don't have enough kinetic energy. They haven't reached the minimum kinetic energy needed for the reaction to occur. On the second case, for our second case, the same reaction running at higher temperature, at temperature T2. So we are increasing the temperature of the system. Notice that at higher temperature, we have more molecules with higher kinetic energy. So the area under the curve within this range of kinetic energy have more particles. So if you compare to the previous one, the number of particles increased, having higher kinetic energy went up. It's moving to the right on this diagram. But also notice that at temperature 2, we have bigger portion of molecules that reached and exceed the minimum energy needed for the reaction to occur. So there are more chances. At temperature 2, the diagram is showing that we have more molecules with more chances to produce effective collisions. Therefore, to make more products. You see how important is this diagram, and we need to understand what is the meaning of that. Transition state theory is another model that explain or try to explain what happened with the molecules when they are reacting together. And we use potential energy diagrams to understand that, because a transition state in a diagram is a hill of maximum potential energy. So let's study a potential energy diagram. When we draw a potential energy diagram, we show on the y-axis this is the y-axis here. We have potential energy. Potential energy increases that direction. We're talking about potential energy in a chemical reaction. In a chemical reaction where we have reactives and products. So let's say we have A plus B forming products. reactives and products. And we know this reaction can either release energy or absorb energy. So the reaction can be either exothermic, when delta H, standard of the reaction, is negative. For an exothermic situation, when the reaction releases heat, releases energy, or this reaction can be endothermic, when delta H standard for the reaction is positive. So we need to draw two different potential energy diagrams for every case. So let's start to draw a potential energy diagram for a exothermic process, like this one. In a exothermic reaction, reactives A and B have higher potential energy than products. So the difference between these potential energies is delta H of the reaction. And that is the amount of heat released during that process, A plus B to make products. So this is a exothermic process where delta H is negative. These type of reactions have a tendency to form more stable products, because the products resulting from this type of reactions have lower potential energy. Compare the potential energy of the products here with the potential energy of reactives here. So the potential energy went down when the reaction goes from this state, independent molecules, to form a product with lower potential energy. So usually those are more thermodynamically stable. Let's analyze what happened, or what needs to happen to go from reactives to products. A and B during that process. As you can see, this potential energy diagram is showing a hill to go from this step to this state. From here, we have the particles. We have two states here and products here. So we need to bring these particles from this state to this state. But notice that we have a barrier here, the hill. That hill represents an increase on the potential energy of the system. So that means A and B needs to reach that hill. And that hill is what we call the transition state. Right top of the hill, That is what we call the transition state. Is the maximum potential energy. It's a maximum. So before A and B forms products, they need to reach the point. And the difference of energy between this transition state, this maximum, and the potential energy of the reactives is what we call the activation energy. It's a minimum of energy needed. So basically you need to give some sort of energy depending on the reaction. Some reactions just need heat. For other reactions, just given energy in light, for example, electromagnetic radiation, microwaves. Others may gain the minimum energy by sound. Sound moves energy too. Sound is another form of energy. So any form of energy, you need to give that energy to the system to activate particles. So when you increase the energy of the particles, what happens is A and B starts to increase their potential energy, vibration, they increase speed, moving faster, increasing chances of collisions, and relate this concept with the previous diagram, Maxwell-Boltzmann energy distribution. So particles are, you increase the temperature of the system, particles A and B starts to move faster because they start to gain kinetic energy. And faster, you increase temperature, they move faster and faster. So they are gaining more kinetic energy. It's transforming, in this case, from potential energy to kinetic energy because you are giving heat to the system. So they move faster and faster. The faster they move, the chances of good collisions will increase. They move faster, so they start vibrating also until they reach this transition state, until they reach this position. What happened at this position? At this position, both particles have enough energy to form something that we call the activated complex. What is an activated complex? An activated complex happens when all bonds are partially broken and new bonds are partially formed. So they reach the right amount, just the right minimum amount of energy to partially break the old bonds and to partially form the new bonds. That is what we call activated complex, and we represent it using square brackets on top of the hill. At that moment, it's just matter of reaction to finish. because now most at that temperature, when they reach the right activation energy, most of the molecules, probably not all molecules, but most of molecules, if you can recall the previous graph here. At that temperature, most of a lot of molecules will have reached that. You keep increasing temperature, so that means we can predict the prediction. You can make a prediction what will be the shape of the system when you increase to a higher temperature, higher than T2. So you can say probably the new shape of the new higher temperature will be here. So a higher temperature, as you increase temperature, now you have more molecules reaching that minimum energy needed, the activation energy. Probably not all molecules have reached that, but you have a big portion of molecules now having effective collisions because they have enough activation energy, providing also they collide with the right position, the right orientation. And now, once this position is reached and the activated, we call this activated complex. And we draw it using square brackets right on top of the hill on the transition stage. Once that position is reached, it's just a matter of time. This is the reaction coordinate or reaction time. So it's just a matter of time. The system will go by itself because this is when you go up and you have high potential energy. Now it's easier to go down, like on a roller coaster. You don't have to do anything else. Gravity in a roller coaster will bring you down. Here, energy will bring you down. It's a natural tendency for systems to go down in the energy hill when we have that gradient, energy gradient. Going from high potential energy to lower potential energy to form more stable products. It's a natural universal tendency. Later on, we are going to include another natural tendency, which is the entropy. We'll discuss that on our thermodynamic chapter. So at least the reaction now is making products with lower potential energy and will release the extra energy here, delta H. This delta H has negative sign because it's energy released by the system. System releasing energy to surroundings. And we said this process, this reaction is an exothermic reaction. Let's analyze what will happen when we have a endothermic process. Now, this potential energy diagram is showing only one step process. This diagram is assuming that A and B goes to product only during one step. From here to there, only one step. Reactions can go from reactives to products in one step, or 2 or 3 steps, or more steps. When you show those steps, those individual steps during the chemical reaction, and that's what we call the reaction mechanism. We can have a situation like this for a potential energy diagram. Remember, potential energy diagram has potential energy here increasing, and we have time. That's the reaction coordinate. For exothermic reaction, always reactives with higher potential energy and products with lower potential energy. So those are reactives. And the products will be here at this potential energy level right here. So this reaction may go through 2 different steps, right? First hill, first activation energy, and then probably goes to a second step. So here we have activation energy for the first case, first step, and also activation energy here for the second step. So we call this activation energy 1, and this is going to be activation energy for the second step, or 2 or 3 steps. So you need to represent a hill per step in your potential energy diagram. We'll discuss this later. Let's analyze the case of endothermic process. For a reaction A plus B to form products, notice that in this case, A and B are here, the reactives, with this potential energy level, whereas products are here at this potential energy level. So you can conclude from here that products have higher potential energy than reactives. So that means the reaction absorbs energy when going from reactives to products. And that's why we say delta H standard for that reaction is positive. So let's see what happens when A and B goes to form products in one step. In one step, we see only one hill. Because again, A and B needs to gain enough energy, needs to reach at least the minimum potential energy needed for A and B to react together, to break enough energy to break all bonds and to form the new bonds of your product. To break all bonds of reactives to form new bonds on your products. And that is all about chemical reaction. That's exactly what we call chemical reaction. Chemical reaction is just that, breaking bonds to form new bonds. Energy is involved in the process. So you increase temperature, for example, or light, or electromagnetic radiation, depending on your reaction. You start to increase temperature and molecules start to move faster and faster and faster. And now they start to collide. Maybe not all collisions are effective because they don't have enough orientation. And nothing is happening here, no reaction. Why not? Because they don't have, molecules are colliding, yes, but they don't have enough kinetic energy. They collide, but that collision is too weak to start breaking bonds and to start forming bonds. But when reactives reach this energetic state here at the transition state, they will start to partially break all bonds and partially form new bonds. So at that state, the all bonds starts to get weaker, 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 to that point that with just a little bit more energy, that all bond is gone. And the new bond is formed. And that is what produce or make the products. So at this position that we call the transition state, we have the activated complex because the reactives reached the activation energy, the minimum energy needed for that particular reaction, needed for those particular reactives to form the new bonds. And that activation energy is the energy difference from the heel, the transition state, and the energy of reactives. That difference of energy is what we call activation energy. And now products are formed. And the difference of energy between products here and reactives is what we call delta H of the reaction. For this case, it's going to be positive because notice the products have higher potential energy than reactives. So that difference of energy absorbed, in this case by the reactions, is called delta H of the reaction. And it's going to be endothermic process. So potential energy diagrams helps to show how energy is moving through the process. If the reaction is occurring in one step, you show only one heel. If the reaction is occurring in 2 steps, so you need to show 2 heels in the potential energy diagram and 2 different activated complexes. If the reaction is moving through 3 different steps, So you need to show 3 different hills in your potential energy diagram. I've been talking about activation energy. How do we calculate activation energy? How do we measure? This is a really important number to know. How do you know what is the minimum energy needed for the reaction to occur? So you can have a successful, you can give the right conditions, thermodynamic conditions to favor the production of products. It is redundant to make more products. So here is the answer. If we plug, you run an experiment and you're actually going to do it. Well, you will see the demonstration how to do this experimentally. That's going to be one of our next labs, demonstrations. And we are going to collect some data. And we are going to plug that data. And we're going to graph. If we draw a graph of natural log of K against 1 over absolute temperature. Absolute temperature has to be Kelvin. So how do you get this? What is K? Here, this is lowercase k. What is K? That is the rate constant. So for a reaction, A plus B to form product, the rate law for that reaction is equals to rate constant times concentration of A times concentration of B elevated to the exponents M and N. The orders of the reaction, M with respect to A, and the order of reaction N with respect to B. So we have here the rate constant. Remember, this constant is temperature dependent also. So if we run the reaction A plus B at different temperatures, let's say absolute temperatures. In the lab, we are going to run it using 2 low temperatures. We are going to use the 2 low temperatures are going to be close to 0, let's say 0.5 degrees Celsius, and then we convert this into Kelvin, right? This is in degrees Celsius. And then another low temperature, we try to keep it somewhere around 2 degrees Celsius. The other temperature is going to be a room temperature. In our labs, room temperature is about 22 degrees Celsius. With the AC on in the room. And at 2 higher temperatures, usually these 2 temperatures are with warm water, hot bath, 65. I'm just throwing some of the most common numbers. And the other one, let's say 70 degrees Celsius, around there. So we'll have 5 different temperatures. Then we convert those temperatures into Kelvin. We convert this into Kelvin, put it there. And we measure, since the previous experiment, and you will learn also, we found graphically the values of M and N, and we know the concentrations we are using in every experiment. In our case, it's going to be experiment number 3. All this run using exactly the same concentrations. We are not changing here concentration, we are just changing temperatures. So we will use experiment number 3 from our lab protocol. We plug these numbers, these concentrations, we can calculate different values of K. So K, the rate constant, is temperature dependent. If you change temperature, then you are going to find different temperatures. At these different values of constant at different values of temperatures. So now we found 5 different values of rate constant at these different values of temperatures. Here they are written in Kelvin. And then you make another column. You make another column that says natural log of temperature. Sorry, natural log of K. Natural log of K. So you take this number, plug that into your calculator, find natural log of that, write it down here. Do the same thing for this, and here, and here, and you got 1, 2, 3, 4, 5 points there. And the next, you need to make another column to find 1 over K. So you make another column there. I cannot make it here. Maybe I do. There you go. You make another column that says 1 over temperature, absolute temperature. One over absolute temperature. So you take this number here, Kelvin, do 1 over that temperature, and you get the number here. Then here, and so on and so forth. You do the same thing for every temperature. Now we have the data table, including natural log of K, the inverse of absolute temperature, and then you graph that here. Just plug that into your program. You can use different programs. You can use the spreadsheet on your computer. Plug these numbers and graph it. a graph of natural log of K in the y-axis and the inverse of absolute temperature on the x-axis. And you will see a nice and beautiful straight line tendency. With negative slope. So go in that direction. From here, and if we use the straight line equation, y equals mx plus b, you will notice that y is natural log of k equals, this is natural, this is y equals m, which is negative k, and that happens to be activation energy over R, the universal gas constant written in joules, joules Kelvin mole, times X, which is 1 over absolute temperature, plus B. And what is B? B happens to be here. This is the y-intercept. I'm going to write a B here because later on we're going to discover that B is the y-intercept. In this case, it's going to be natural log of K at time 0. And that's going to be a constant for that experiment. And then we are going to replace that constant by A. This experiment was done by a chemist called physical chemist Arrhenius. That's why we're using letter capital A here, and that's going to be the constant for that process. So what is the important thing here about this relationship we found here? The m, which is the slope of this line, and you can find when you do graphical analysis, you plug this, you do graphical analysis. Graphical analysis will calculate for you the b-intercept and will calculate for you the slope. In this case, the slope is negative, right? Because we have a negative slope, and happens that that slope equals negative activation energy over R. And we can use this information to find experimentally the value of that activation energy for that particular reaction. Now you can rearrange this formula. We can play with this. We can take natural log on both sides, etc. We can play with this reaction and have different shapes. for the equation. This is another shape, probably this is the most common shape of that Arrhenius equation. And still, because this already solved for K. So we can use the rate, we can find actually the rate constant if we have this information, but most of the times, calculating the rate constant is a lot easier using the experimental results, and then using this value already calculated to calculate the activation energy. So then we plug everything here, solve for activation energy, we can calculate the activation energy. If we know the rate constant and we know the temperature, this is another constant. And here, notice that we included a factor here, which is a constant, the one I was mentioning before, capital A, and that is called a frequency factor or pre-exponential factor or Arrhenius constant. This factor includes or takes into account the variables like orientation of molecules and effective collisions during the process. Another way to represent this equation is exactly the same equation we got from here. Let's see from here. We got this equation of this one can be represented like this or like this. It's exactly the same equation, just playing around, moving it around. We can get this. Probably this is the one that you are going to use most of the times. It's a lot easier to work with this than the previous one, especially when you're trying to find the activation energy. And the problems I'm going to give you and we're going to solve will be using this form of the equation, because the problem will give you two different rate constants from one initial state and one final state, and will give you the temperatures for this state. So this is the rate constant at temperature 1. And this is the rate constant 2 at temperature T2. The only thing you need to remember is that these temperatures, when you plug these temperatures here, they must be in Kelvin. If you forget to convert whatever temperature is given in the problem, Celsius, Fahrenheit, if you forget to convert that into Kelvin, capital K, temperature, then you will get the wrong answer. So don't forget, here you must plug Kelvin temperatures. So problem will give you this temperature will give you the two values of rate constants. Just find the natural law, plug here, and then solve for activation energy. R is the universal gas law in joules, Kelvin mole, and kilojoules. This is one example how to apply the formula. For a given reaction, the rate constant goes up by a factor of 1.65 when you increase temperature from 20 degrees Celsius to 40 degrees Celsius. So this problem also is giving you some extra information that when you increase temperature of the system, the rate constant goes up too. So we have two different temperatures here. So we have 20 let's label this temperature 1 is 20 degrees Celsius, and temperature 2, 40 degrees Celsius. So temperature goes in that direction, went up. And the rate constant was measured. And it says this ratio, when it goes from this temperature to this temperature, the rate constant goes up by a factor 1.65x. This is x. That's the rate. But you can show this in a ratio too. You say the rate, sorry, talking about the rate constant, so I should put the, not the rate constant. In other words, the ratio, and this is K2, K1. K2 over K1 is 165. That's the meaning. What temperature is this? In Kelvin. So that's 293 Kelvin. And this is 313. And you add 315 to 273 Kelvin. Now we have the data. We just need to plug that into this equation here. When you plug everything, natural log of 1.5, which you already have the ratio. Sometimes the problem gives you the value of this and gives you the value of that, so you need to plug that here, K2 over K1, then you take natural log of that fraction, plug the two temperatures, work it out, and solve. Value of R is 8.31. That's a constant, we already know that. 8.31 joules Kelvin mole, joules per Kelvin mole. And this is another very important fact. Depending on the unit you are using, the units of the R, you will get answer in kilojoules or joules. This one, we are using times 10 to the -3 kilojoules per mole Kelvin. If you want to write it this way, moles -1, Kelvin -1. So we're using a units of R in kilojoules. If you use joules, then your answer will be in joules. 8.31 joules per Kelvin mole. And you plug that and you get your answer. Now we know exactly what is the activation energy for that. You need to do this calculation also using the data given in the lab report. However, and you can do this, apply this formula, because in your experiment, we will have, you pick any two temperatures and any two values of rate constant and plug that into the formula. Yeah, into this formula. to find activation energy, because that's one of the questions you will have, and you need to answer that in your lab report. However, there's another way to do it. Thanks to the fact that when you graph these numbers, and you need to do it in your report, you need to graph these numbers and print it out. Also, you need to do graphical analysis. When you do graphical analysis, as I mentioned before, the graphical analysis will do it for you. Will give you the value of B, and will give you the value of M, the slope. And you know that the slope M from your graphical analysis of the curve equals negative activation energy over R. So activation energy from here, you solve for activation energy, is going to be activation energy equals negative M R. This is the slope. Obtained from your graphical analysis. Easy. How easy is this? Can be easier. Just plot your data, experimental data, this experimental data into here, get this nice straight line with negative slope, do graphical analysis. Of course, you need to do the graphical analysis too, and the computer will show you a box here, will show you a box, but you ask the computer to show you the box and show you the straight line equation. It will show you the values of M, and it will show you the value of B, and also the correlation. The correlation should be around 1 or close to 1. If you have a nice straight line, 0.9999 is a good correlation. But the computer will do it for you, your graphical analysis. Just take the number, the slope, plug it here, and voila. You just found the activation energy. Just don't forget to work out the units. Activation energy units are joules or kilojoules. Since usually those are big numbers, you want to represent that in kilojoules. All right, that's how you work the Arrhenius equation. The next is the reaction mechanism. What is a reaction mechanism? It's a molecular description of the sequence of events or individual steps that happens at molecular level during the chemical reaction. In other words, you need to write down every steps, all the steps happening at molecular level when reactives A and B forms product. And every individual step reaction is what we call elementary reaction or elementary process. When we add all these elementary steps or elementary reaction in the mechanism, we should get a balanced chemical equation for the overall reaction. I have one example here. This is a very classic example of a reaction mechanism for the reaction of methane with chlorine at high temperatures, around 400 to 450 degrees Celsius. This is a chain reaction, where it shows the first step, which is the formation of radicals. And this is a slow process. It is a slow process because this needs to go through a high heat during that process. That means they need to gain enough, the molecule needs to gain enough kinetic energy to break down into two radicals. We have here, we can represent this step as follows. So we have chlorine, Cl2, like that, where this line here represents a covalent bond between the two chlorine atoms. This chlorine here is sharing the electron. Remember that chlorine have 7 valence electrons, and this chlorine also have 7 valence electrons, and this is the 7th. And they are, in this molecule, they are sharing this pair of electrons. So the system needs to provide enough potential energy so chlorine Cl2 gas gains the energy needed to bring this molecule to form an activated complex, where this bond is partially broken. It's ready to break. Right there. To form the radicals, and that radical will be Cl dot, 1 electron. This is a homolytic fracture of that bond, forming the radicals. Radicals are very unstable species. This process is slow because the reaction needs to bring energy from this potential energy state to this potential energy state. So the molecule Cl2 needs to gain enough activation energy to get there. Once the molecule reaches the transition state, forms the activated complex, and now is free, making two Cl dot radicals, which is again very unstable, and that will react very quick with another species. The second step is the propagation step. So notice that this reaction can be described in 2 different steps. First step, second step. Actually, here we have another step. And here we have more step. Those are just possibilities of what can be, sorry, what can happen at the termination step. So we represent the whole reaction in different steps. Every step shows or proposes what's happening at molecular or atomic level. Sorry about that. When we add all these steps together, we should get the overall reaction, overall balanced reaction. So this reaction is the reaction of chlorination of methane gas, CH4 plus Cl2, to form CH3Cl plus HCl. Another example I have here, this is the chloromethane, which is an haloalkane compound, an organic compound. How important is to know the reaction mechanism? Well, the reaction mechanism helps to understand what's going on at molecular level during the reaction and help us to make improvements in the process. If you can discover a new reaction mechanism for a reaction to improve the production of material, that may represent at industrial level a lot of money. Some reactions that goes through one process are slow, but if we can modify the reaction or adjust the reaction to go through a different mechanism, that will improve the formation of products. At the beginning of the chapter, I was mentioning that the rate of reaction can help us to figure the reaction mechanism. This is one example. We have this elementary process. Remember, elementary process is just one step of the reaction mechanism. This whole process here represents the reaction mechanism for this reaction on the bottom. Represents the reaction mechanism for the chlorination of methane to form CH3Cl plus HCl, chloromethane and hydrogen chloride. And we represent that mechanism using different steps. Steps 1, 2, 3, 4. And every step of those is called an elementary step. So every elementary step shows only one part of the process. Here we have an example of one elementary step. From this elementary step, we can write the rate law for that elementary step. Here is the new thing, and also a good news for you. When you find or you write the rate law for an elementary process, or elementary step like this one. Remember, we write the rate in terms of concentration of products, as we have been doing before. So it's going to be rate equals rate constant times concentration of NO. And here, elevated to this power, which is this stoichiometric coefficient. So here, the order of this reaction is second order. And we get this number from here. I know some of you already jump on a screen saying, wait a minute. You said before that the order of the reaction, those little exponents in the rate law, can be determined only and only from experimental data. My answer is yes, you're right. The rate law of an overall process, overall reaction, can be obtained only from experimental data. However, the order of the reaction with respect to one of the reactives from an elementary step or elementary process can be obtained from its stoichiometric coefficient for that particular elementary process only. And this is the only exception we have. So you need to keep that in mind. If you have elementary process, you can use the stoichiometric coefficients of that reactive, and that will be the order of the reaction with respect to the concentration of that reactive. I'll give you more examples. Again, you can do this only if you have an elementary process. You cannot do that if you have an overall reaction. For the overall reaction, you need to run the actual experiment. But this is the beauty of this process. If this rate here, the rate law for elementary process, matches the results, the experimental result, that means your reaction mechanism is accurate, is valid. So we can assume, or we can take that reaction mechanism and we can accept it. If the rate law of your elementary process does not match that rate law of the overall reaction, then your mechanism is not acceptable and you need to write a different mechanism. Remember, reaction mechanism is just a proposal trying to explain what's happening at molecular level. You don't see, you actually don't see the atoms or molecules there. At subatomic level, we just see properties and changes during the reaction at macroscopic level. We can take measurements and we try to explain what's going on at molecular level by writing reaction mechanisms. So this is one way, a very good way to test your proposal, your reaction mechanism. I'll show you one more example. when we have multi-step reactions. Most of reactions are multi-steps. That means they go through different steps from reactives to form products. Some of these steps can be slow, others can be fast, depending on the nature of the reactives, depending on the type of chemical bond, depending on the activation energy involved, depending on the conditions you are giving to the reaction. Some steps can go fast than others. Some steps can go slow. And we said that the slowest step of your mechanism is the rate determining step or rate limiting step. Again, since steps in the reaction mechanism can be fast or slow, some of them will go fast, some of them will go low, or one of them is going to be very low, will have low rate, will go slow, and other steps will go fast. During that transition state, usually the steps that requires a lot of activation energy, they will be this slow, right? Because they need to wait, and you need to give the energy, and they gaining energy until they reach the transition state. So if the reaction has a multi-step situation, like for example, this is time with a little curve over there, which is now intentional. We have potential energy here. This is a potential energy diagram. This represents here an exothermic reaction for a multi-step process. We have reactives here. Reactives, A plus B, let's say plus C, to form products. Products are here. And the reaction A plus B plus C to form product. And from here, just by looking at the graph, we can say this reaction is exothermic, because products have lower potential energy than reactives. So on a multi-step process, we can think, let's say, first step could be something like that. And then one more step. And then another step here, until finally forms the products. So let's check activation energies. Here, how do you measure activation energy in this graph? Find what is the energy, potential energy of reactives. And this is the first hill, the first transition state. So this difference of energy will be your activation energy for step 1. For step 2, this difference of energy here will represent the activation energy for step 2. And for step 3, this difference of energy between this base and the peak is activation energy for step 3. This is the, for step 1, this is the activation energy for species involved in that transition. Probably in this transition, for example, involves only A and B, and C is doing nothing here so far. It's waiting. So this is going to be the activation energy for participants of the process between A and B in the activated complex. Maybe A and B forms a different species. For example, if our first step will be A plus B to form D. First step, and goes through this process. So what is the product here? Is D. This is a partial product as a result of the reaction of A and B. So new species D will show up during the process. And then this species D needs to be activated to react, let's say, I'll just give you an example, with A to form the complex D plus A. It's going to partially break bonds, and it's going to partially form bonds between D and A. And this activation energy 2 represents the activation energy of this species here participating on this step only. And let's say, okay, so the second step then is going to be D plus A to form let's say dA. Let's say to form E. That will represent this step here. So the result of this reaction will be E. And then E will go through a third step, or the reaction will go through a third step where E reacts with B to make the final product. So E needs to gain enough energy, and that's going to be activation energy 3 for that step to form here the activated complex, E, B. And once this is formed, it's going to make the product. So notice that we have different activation energies because we have a multi-step process. And we, on the potential energy diagram, is showing 3 different hills representing every different step. Every step of this is called elementary process or elementary step. From here, if we compare activation energies, we can say which one is the highest. What step has the highest energy? So I can say probably this is the highest. I meant to write this highest. So let's say this activation energy is higher than this, and this is higher than this. This is the slowest, or no, sorry, not the slowest, the lower activation energy of all. So let's assume this here looks the same, I know. But let's assume this activation energy 2 is higher than this. That means this hill is much higher, or is a little bit higher than this. What do you say about the speed of this process to go from D and E? The speed of the second step. Since it needs to climb a higher hill, it is correct to think that this is going to be the slowest. It's going to be, and you write here, a slow step. Why? Because it has, that's the one that has the higher activation energy, the highest activation energy. This is the one with the highest activation energy. It's the slowest because it has the highest activation energy. And this one, step 1, is going to be what, fast or slow? It's going to be fast because it has a low hill to go up and down. So that reaction very quick will reach the activation energy, the transition state, so it's going to be fast. Let's say very fast. And this is going to be fast too. And we say that the slow step, or the slowest step of the process, is the rate limiting step. Rate limiting step, or rate determining step for the whole reaction. Does it make sense? The overall reaction speed, or the kinetics of the overall reaction, will depend solely on the rate limiting step, which is the slowest step of the whole process, of the whole mechanism, which is the one that has the highest activation energy. I used to represent the situation like the inline production factory. Let's say this factory makes shirts and it's a line production. So the first worker, for example, draws, designs. The second worker cuts the fabric. The third worker, what is the job of the third worker? Let's say put buttons. The next worker sew one piece. the next worker saw the packets, and so on and so forth. But one of the workers is the slowest during that process, only one, because what this worker is doing requires more attention, more precise work, more focus. This person cannot rush. He needs to take the time to make nice shirts or to complete his work. What's going to happen? The speed of production of shirts in the whole factory depends on the speed of this person. The first worker, second worker, any worker behind, which is doing something before him or her, they can be fast doing their jobs. And the materials start to pile up in front of this very specialized worker. He or her needs to take a lot of time to complete his task or her task. Once this person finishes his part, he moves the material to the next person, and the next person can do it very fast, and the next one fast, and so on and so forth. So workers before him or her can be fast. Workers after him or her can be fast, but this worker in particular cannot do faster job because the nature of the work. So the whole production, the speed of making shirts will depend in the speed of this worker. And that's what we call the speed limiting. Speed limiting. For a reaction will be the speed limiting step. And that's important to recognize the step, because on that step, you can find the rate law for that step, and that rate law for the slowest step should match the rate of the overall reaction. In this example I created here, notice that this is the overall reaction. A plus B to make products is this one here, which is exothermic. Notice that on this overall reaction, we don't see these species, D and E. They are not here, they are not written in the overall reaction. They are not part of reactives, they are not part of products. You don't see D and E here, because they are partially formed here and then they are consumed in the process. And here they balance stoichiometrically, so they cancels out when we add this. When we add these three steps. So when we add this, we have two A's here, two A's. This should be 2, and this also should be 2 for the following reason. And here on reactives, we have B here, and also we have B here plus 2B to form products. Notice that D is not here. E is also not part of the overall reaction. They just form and go. Similar happens with E. It forms and then is used up. Forms and go. These species that can show up during the steps but are not part of the overall reaction are called intermediates. They are not part of the overall reaction. They are not part of the rate law. And we said that when we write the reaction mechanism, we add all the steps, and the sum of all steps like here should match the overall equation for a balanced reaction, balanced equation. So notice that here we got exactly the same we have here. Even more, let's say the rate law for this is rate constant times concentration of A. Experimentally. Using experimental results. Experimental rate law for that particular reaction is this from experiments. And then we propose this mechanism. And then we use the rate limiting step, which is the second step, to find the rate law for that experiment, for that step. So let me rewrite step number 2 here from this one. Step number 2 was D plus A to form E. And this is an elementary step of the mechanism, but not any elementary step. This is actually the slowest step, the slowest step, the slowest elementary step of the mechanism. So you take that out and you write the rate law for that step. So the rate law for this step equals rate constant times concentration of, we don't write D, we don't write E. Why not? Because this is not part of the overall reaction. This is A, what was the name of this? D and E, an intermediate. So you say here somewhere, it's important. If intermediates here, species are D and E. They are formed during the steps and they are consumed. That's why they don't show up as a reactives and they don't show up as a products. So we have to write the rate in terms of A. And what is the order of this? Step is 1. Because you can take, since this is an elementary step, and only on this case, because you have elementary step, you can take the order of the reaction with respect to the reactive from here, from the stoichiometric coefficient. That's the only chance you can do. You can do that. This exponent here comes from here, from the stoichiometric coefficient of a elementary step. Again, you cannot do that here because this is the rate of the overall reaction, and that has to be done experimentally. And this is the rate for that step. If analysis, if the rate law of the slowest elementary step matches the rate law, the experimental rate law of the overall reaction, then your mechanism is correct. Proposed is acceptable. So you say, yes, this mechanism is accepted, and you can write it down, and you can publish it, and you say the reaction of 2A plus 2B making this product follows this mechanism, and you can publish it. And here is the demonstration. If you propose this mechanism, and this mechanism and the rate law from the lowest step of that mechanism doesn't match the experimental rate law for the overall reaction, then your mechanism is not good and you need to write another one. To explain another one. Of course, everything is done through experiments to verify your steps. But you have to write a new mechanism. So that's the importance of the mechanism, and that's why at the beginning I said that the rate law will help us to find or to write reaction mechanisms. This is one example. This reaction of 2NO plus 2H2 to form nitrogen gas N2 plus 2H2O is an overall reaction. This is the overall equation. And it was found, somebody conducted the experiment, it was found that the rate law for that reaction, for the overall reaction is K, the rate constant, times concentration of NO to the second power times concentration of H2 to the first power. That's an experimental rate law. From that experimental rate law, we can conclude that the reaction is second order with respect to concentration of NO, and the reaction is first order with respect to H2. It's very important to do the analysis. When you see the rate law, you need to extract that information from what is written there. It is second order with respect to NO and it's first order with respect to H2. What is the meaning of second order? Second order means that the concentration of NO affects the speed of the reaction. How? Every time you double the concentration of NO in that reaction, the speed quadruple. That's second order. You double the concentration of NO and the speed quadruple, that means the reaction is second order with respect to the reactive. And the reaction is also first order with respect to H2. What is the meaning of first order with respect to O2? H2. It means that when you double the concentration of H2 in your reaction, the speed also doubles. The speed goes up, speed up by 2 times. If you double this concentration and the speed of the reaction doubles, that means it's first order. Very valuable information. But also, it's telling you something else, the molecularity of the reaction. Second order reaction with respect to NO, that means it makes bimolecular collisions. By the molecularity is 2. Bimolecular means during the transition state, 2 species are colliding and forming the activated complex. This is really interesting. This is very valuable information to write reaction mechanisms. So if we draw a potential energy diagram, against time on a system that is exothermic, you can do this also for an endothermic process. I like exothermic process. So let's draw an exothermic potential energy diagram. Let's say this is running, how many steps here? I think I have the steps for this. 1, 2, 3 steps. This reaction goes actually through 3 steps according with the mechanism. Mechanisms are not absolute. You can run your own experiment in your research lab and find a different mechanism that explain better that reaction. So over the time, mechanisms can change. So if this one goes through a 3 mechanism, and now I want to take this chance to show you how to write the potential energy diagram from the mechanisms. I'm going to do it again here. Let's do it here. I need more room. Why I need more room? Why do I need more room? To write or to draw the potential energy diagram. Guess why? Oops. All right. Okay. What coordinate is this? Potential energy. What coordinate is this? Time. Or reaction coordinate. We have reactives. Let's put reactives somewhere here with this potential energy, initial potential energy. In this case, our reactives are 2NO plus H2, 2H2. So we have initially 2NO plus H2. all reactives there, ready to work. And the products, what is the product of this reaction? N2 plus 2H2. So the product should be somewhere here, since we have a potential a exothermic reaction. That should be somewhere here. The products are N2 plus 2 waters. What happened here? From here, from the initial state, when you put the reactives together, and here, when you get the products, something must happen at molecular level to get these products. And that is what we're going to show here, and that's going to be your mechanism. It was found, it's proposed that this reaction goes through a 3-step mechanism. The kinetics of this reaction goes through a 3-step mechanism. So therefore, if you have three steps in your mechanism, you must have 3 hills on your mechanism, on your potential energy diagram. If in a potential energy diagram for a particular reaction, you see only 2 hills, that means the reaction has a 2-step mechanism, and so on and so forth. If you have 4-step mechanism, you need to show 4 hills in your potential energy diagram for that reaction. So 3 hills. Now, one is going to be the slowest, and the others are going to be faster. Therefore, one of the hills is going to be the lowest, and the other hills can have a different, they can be higher. My question is, what step has the highest mechanism? Sorry, highest hill? The step that has highest hill is the slowest one. Why? You remember why? Because the slowest one, why is going slow? Why this step is proposed to go slow? Because it has the highest what? Activation energy. The activation energy for this is higher than this activation energy, and higher than this activation energy. So you say here activation energy for step 1, this is activation energy for step 2, and this is the activation energy for step 3. We know this is going to be very high activation energy, higher activation energy. So the higher hill, that's why it takes more time. It's slow to go to cross the hill. So now we know that the second hill has to be the highest. So the first one goes fast, that means a small hill. Now we go through the second step, higher hill. And now we have another small hill. And then finally the product. So it's a 3-hill potential energy diagram that corresponds to a 3-step mechanism. Here, and the first step shows the collision between 2 NO molecules. If you see the rate here, let me write again. The rate for the overall reaction equals K times concentration of NO times concentration of H2. And this is experimental, and this is for the overall reaction. Therefore, it has to be experimental. It shows that the reaction is second order with respect to NO. We already explained what is the meaning of that in terms of concentration. The second meaning of that is the molecularity for the reaction is 2 for this species. That means at the transition state, we have 2 NO molecules colliding each other. That's the molecularity. How many molecules makes part of the activated complex in the transition state? 2. That comes from here. That's molecularity 2. And we said this is bimolecular step. What happened on the second step? And it says, what is the order of reaction with respect to H2? It's 1. We already explained what is the meaning of that in terms of changing concentration of H2 and what happened with this, the rate of the reaction when we do that change. But also it's telling you that molecularity of the reaction with respect to H2 is what? It's 1. Notice that on the first step, H2 has nothing to do with that step. H2 is not working. The product of the first step, as you can see here, is N2O. O2. Now that species is going to work with hydrogen. And the mechanism says that the reaction is first order with respect to concentration of H2, and also the molecularity of the process is 1. That means at the transition state here, how many molecules are participating during the process? Only 1. H2, because molecularity is 1. So this needs to be activated, this bond needs to break down, so that will react with this to form N2O plus H2O. Once this is formed, this is very reactive. And N2O will attack another hydrogen molecule, because remember the molecularity is 1. So this is the basically it's the same one, because at the same time this is being formed, it's going to attack another of those to form the final product. As you can see here, we have this species N2O2 is formed here, but at the same time it's being consumed here. What is the name of this species here? They cancel out when we add them. They are intermediates, because they show us an intermediates during the process, but they don't show up on the final results. They don't show up on the reactives. Did you see another intermediate here? This is also an intermediate, and this is also an intermediate. When we add these two together, we get 2NO plus here we have 2H2 to form. This is an intermediate, we cancel. This is an intermediate, we cancel it because it was consumed. We have N2 here plus 2H2. 2H2O. And that's the overall. That is the overall reaction equation. So we can write we can find the rate law for the slowest step. This is the slowest step. Let's write it down here to prove if we can accept this mechanism or not. So let's rewrite the second step. This is the first step, second step, and usually the mechanism steps are written using these little lowercase I numbers or I letters. All right. So on the second step, we have this elementary process, N2O2 plus H2 to form N2O plus H2O. We can write the rate law for the elementary step right from that information. Rate, very straightforward, times, what is the rate law for this? Just from here, from using stoichiometric coefficients, is going to be times concentration of N2O2 times concentration of H2. That will be the rate law for that elementary step. But notice that you are writing a rate of the elementary step using a species that we just call intermediate, and that species doesn't show in the overall chemical equation. It's not there. So we need to make some adjustments. We just need to play with this a little bit. And since this is an elementary step that shows up and then is consumed, we can take that out and say the rate equals K times H2 . So it shows that it's first order with respect to H2. And then we do the analysis with respect to the initial equilibrium reaction. As you can see here, the first step is showing an equilibrium between these two species. What happened at the equilibrium? What is the meaning of equilibrium? The equilibrium in step 1 for step 1 we have an equilibrium. It's an equilibrium step. Means what? Means that the speed of the forward reaction, the rate of the forward reaction equals the rate of the reverse reaction. This is not B, this is R. The rate. I put it that way. The rate of the forward reaction equals rate of the reverse reaction. That's the equilibrium condition, right? So we can write the rate of the forward reaction for the step number, for the first step. Let me write the first step. The first step says that 2NO is at the equilibrium with N2O2. So let's write the rate of the forward reaction expression. So it's going to be for the forward reaction, it's going to be constant, okay, rate equals constant times concentration of NO. And since this is an elementary step, this is going to be the order of the reaction with respect to NO. And the rate, and this is the rate of the forward. So this is going to be the constant of the forward reaction. Now, the rate for the reverse reaction is going to have rate constant for the reverse reaction times going from here to there. So for the reverse reaction, this is the reactive concentration of N2O2. We reorganize this and we say if this is true, at the equilibrium, rate of the forward reaction equals rate of the reverse reaction. So we can rewrite this and say rate constant of the forward reaction times NO squared equals rate constant of the reverse reaction times concentration of N2O2. So let's write everything and express that in terms of the concentration of our intermediate, because we want to get rid of that. We need to eliminate that because that's not, the intermediate N2O2 is not part of the overall reaction. So concentration of N2O2 equals, we need to move this around, it's going to be equals K sub F over K R times concentration of NO squared. And what is constant divided by constant is another constant. So let's call the constant prime times concentration of NO square. Now we can plug this into the rate law for the second step. So this is going to be from first step, and now from the second step, which is the rate determining step. Do you remember what was that? The rate for the determining step was constant times concentration of N2O2 times concentration of H2, I believe. Here, concentration of H2. Remember, we wanted to eliminate this first term of the rate law because this is not part of the overall reaction. That's why we did all this. So times H2. That is the rate law from second step. Now we can plug, substitute equation from step 1 into this equation. So that's going to be replacing. Let's call this equation 1 into equation 2. 1 into equation 2. So we have rate equals rate constant, this one, times this. What is this? So that is constant prime times concentration of NO square. That was this, which is this, times concentration of H2. But what is constant times constant? Is another constant. It's the rate constant times NO square times H2. And that is your rate law. From this rate law, we found it just from the reaction mechanism. This is from the mechanism. What is your conclusion? Can we accept this mechanism or not? Should we discard this mechanism and say, no, this is not good, the reaction is not going through these steps? The answer is yes. We can accept that mechanism because the rate law from the slowest step of that mechanism matches exactly the rate law, the experimental rate law for the overall reaction. Two different sources. Experimental rate law for the overall reaction matches the rate law of the lowest step of the proposed mechanism. And you need to write that what I said, the analysis. Not just don't leave it there. You have to explain why you are doing this. We are doing this step just to prove that the mechanism can be accepted. All right, this is another example. This is another example of mechanism. It's showing the overall reaction here. It's showing that rate law for that overall reaction. And of course, obviously, this rate is an experimental rate law for the overall reaction. Remember, the rate laws of overall reaction has to be found experimentally. You need to run the reaction, collect the data, and so on and so forth. All what I showed you before. And then the proposed mechanism for that reaction goes through two different steps. What is the question? Prove it. Prove it. Prove that this mechanism can be accepted. Can this mechanism be accepted? Let's see. What do? You choose the rate determining step. Which one is the rate determining step for the mechanism? The slowest one. So from here, we are going to write the rate for that step. So the rate for that step is going to be K times concentration of NO 2Cl. And what is the order of this reaction with respect to this? That since this is an elementary step, elementary process, the stoichiometric coefficient is 1, so the stoichiometric coefficient here is 1. That's it. We just compare the rate of the slowest elementary step to the rate, experimental rate of the overall reaction. If these two matches, so that means your mechanism is good. In this case, yes, exact match. So this mechanism can be accepted. Another question I can add to this is draw a potential energy diagram for the process. For that, the problem should tell you if this reaction is an endothermic or exothermic reaction. I'm assuming this is an exothermic reaction. It's producing a gas, which is a very good driving force. So, for a exothermic reaction, here are the products, here are the reactives, and here are the products. Reactives, in this case only NO 2Cl, and the products NO 2 plus Cl2. How many hills? 2 hills in the potential energy diagram. We need to write to label the axis, potential energy, time. You cannot draw a graph without labeling the axis. Always write the label and also write the name here. I'm not writing it, but I'm saying I'm drawing a graph of potential energy against time or reaction coordinate. That's the name of the graph. We just label the axis. Those details are really important. In an exam, you lose points. If you draw a graph or on a lab report, you draw a graph like this and you didn't label the axis, then you take credits. Same thing, if you draw a graph and you don't write the name of the graph, this is the graph of potential energy against time for the reaction 2NO2Cl to form 2NO2 plus Cl2. That's it. That's the proper way to do it. So how many hills? Let's do critical thinking here. How many hills should we draw in this potential energy diagram? I know your answer was right. 2 hills, because we have 2 steps. Now, what hill is going to be the highest? Yes, the first hill, because it's the one where the reaction goes slow. So highest, first hill, and then a small hill, the second hill, and then forms products. 2 hills, 2 steps. First step is the lowest, the slowest. So that means you have the highest hill because has higher activation energy here in this, during this transition stage to form. And how many molecules are participating in this transition stage? What is the molecularity of that activated complex? From here, we know the molecularity is 1. And also from here, the rate is telling you is first order with respect to that compound. So the molecularity is 1. So only 1 molecule is participating in that. This here should be a lowercase l, not capital L. This is not acceptable. Lowercase. The rule says it's lowercase. I don't know what element is that. Cl, carbon L, I don't know what element is L. But this is not carbon L, it's chloride. So this is, we need to fix that. Lowercase. You notice it before? Great. That means you have a good eye and you have a good concept on chemistry. Congratulations. All right. So this is the first step. The second step goes faster. We don't care about how faster. So that means the hill is slower because it has lower activation energy for the second step. You see, smaller than this, so that it goes faster. And here the species working probably are these two in the for the activated complex there. And you can propose that we don't know for sure N2Cl plus Cl. Oh, sorry, it's not plus, it's just dots that shows partially broken bonds and partially formed bonds. And this, you draw these potential energy diagrams, and it's correct. That represents the mechanism. All right, I'm going to stop here. On the next video, we're going to start solving problems to apply all the equations we just learned here in this chapter. We are going to build problem-solving skills. I'll show you a few tricks, how to work with the equations, how to do an analysis when you are reading the problems. So see you on the next video.